All right, so let's begin. So let's quickly recap what we did last time. So our goal today, or in the last lecture, was to introduce the operator for an infinitesimal transformation. So infinitesimal rotation. So remember that um, any physical rotation in the XYZ or any dimensionality of space really induces a corresponding linear operator in the Hilbert space that then acts on the state vectors. So we are trying to understand the form of this operator for very, very small rotations by a very, very small angle. So so-called infinitesimal transformations, in this case, infinitesimal rotations. So we wrote down the form for such an operator as u of omega. Omega is a rotation parameter, angle parameter, and this by definition a real parameter because angles are real. And we wrote this to be I or 1 plus omega ij jij. So we spent some time in understanding what this equation really meant. Remember that this is summed over two indices ij and omega jij, but it is not to be understood as matrix multiplication. Okay, remember that omega ij is a parameter. So for example, if you look at the example for 2D that we simply wrote down, omega 1, 2 is a parameter that enters the omega matrix. So the omega ij here is not a matrix, but a parameter. The jij is a matrix, but the ij do not refer to the row and column index. For example, j12 in 3 dimensions is one matrix, j23 is one matrix, j13 is another matrix. For example, in the case of 3 dimensions, the way to understand this is j12 is a rotation in the 1-2 plane. Okay. In other words, you can understand this as a rotation around the 3-axis. So we will take recourse to a very simpler notation in a short while. Similarly, j23 is a rotation in the 2-3 plane, or equivalently a rotation around the 1-axis. And j13, as you can easily guess, is a rotation in the 1-3 plane, or equivalently a rotation around the 2-axis. And the jij is completely antisymmetric in the indices I and j, because the omegas are antisymmetric in the indices I and j. And we wrote down how such an operator transforms different other operators. For example, if you have a vector operator vi with, let us say in 3 dimensions, the vector operator has 3 different components, v1, v2, v3, then the action of rotation mixes the different components of the vector operator. Okay, that is the equation over the curly braces. So now our goal is to try and understand what this means if u is an infinitesimal rotational transformation. So we wrote down the corresponding equation in the last line, so we will pick it up from there. Okay. If there's any questions at this point, you can ask. Otherwise, I'll move on with this particular equation. So our goal is to translate this equation that is valid for, so this equation u dagger VIU equals RIL VL is valid for any finite rotation. So we want to understand what this particular equation means if the rotation that we are doing is an infinitesimal rotation by a very small angle. And we will see something that you will see in physics over and over again, that any symmetry generator, any symmetry transformation can be, the physics of such transformations can be understood via a set of commutation relations. Okay, so commutation relations with some physical observations. So let us see what the commutation relation of J is with some other operators, some other observations. Okay, this Vi could be any vector operator, for example, position, momentum, whatever. All right. So let us start with this equation. I'll rewrite this equation. So from u dagger R, Vi u of R equals RIL VL. So let us evaluate the left-hand side and right-hand side separately. The left-hand side of this equation, as I have just written in the line above, is I minus omega KL JKL. The minus because I'm doing a dagger, okay? And JKL doesn't change sign because I expect the generators to be Hermitian matrices because they are symmetry. We want to understand symmetry operations. VI I minus, sorry, I plus I over 2h bar omega KL JKL. Okay. Now remember that we are sticking with first order in omega. Omega is a very small parameter. So when I evaluate this multiplication, I will throw out any factors that is quadratic in omega. So the first term, obviously, so let's do this carefully because these are operators. Remember that omega is not an operator, but J is an operator and B is an operator. So order matters. So I'll keep this guy the same. And I will write this as VI times unit operator is just VI plus I over 2h bar. Omega is just a number, so I can pull it out. And this is equal to VI times JKL because VI is multiplying J from the left. So now let us evaluate this. The first term is just I times whatever. So it's the exact same thing again. So this is VI plus I over 2h bar omega KL VI JKL. The second term is minus I over 2h bar omega KL. Remember this time JKL is to the left and VI is to the right. So I'm multiplying this with this. So this is equal to JKL VI, and the multiplication of this with this is quadratic in omega. I get omega KL, omega KL. Omega KL is an omega IJ. So this I will safely neglect since I'm only working to order omega. Okay. There's these lines. Okay. So what is this equal to? I can write this as VI plus I over 2h bar omega KL times VI JKL minus JKL VI, which is the commutator of VI and the rotation generators JKL. So ultimately the left hand side is boiled down. If I look at it for infinitesimal rotations, it has boiled down to the commutation of the operator VI under question with the rotation generator JKL. Okay. Now what is the right hand side? The right hand side is RILVL, which for infinitesimal rotations is equal to delta IL plus omega IL times VL. Okay, so remember that this is exactly what we talked about when we talked about infinitesimal rotations. Rij can be understood as the unit matrix plus some small rotation angle omega. So this obviously is equal to the delta ILVL is equal to VI because the delta Kronecker delta forces L to be equal to I plus omega IL. So equating the left hand side and right hand side, we have I over 2h bar omega KL times VI JKL equals omega IL VL. Okay, remember that the VI in the left hand side cancels the VI on the right hand side. So ultimately, this is boiled down to an equation that tells you what the commutator of V and J is. Well, almost. There's also omegas that come along for the right, and we typically won't like to have them in the commutation relation. Okay. Why? Because a commutation relation is something that is fundamental, that is always true, regardless of whether I rotate by 10 to the minus 50 degrees or 10 to the minus 35 degrees, or any other small rotation. Okay, so typically I would like to have an equation that only tells me the commutation or commutator of V and J without any omegas coming for the right. The way I can, of course, there is too many integers here floating around, so I have to be a little careful. Now, if I had omega KL on the left and omega KL on the right, then I can simply say that for any omega KL, this has to be true. But unfortunately, I have omega KL on the left and omega IL on the right. But I can fix this. First, notice that since omega is antisymmetric in I and L, I can write this as 1/2 omega IL minus omega LI times VL. Why? Because omega LI is just minus omega IL, and omega IL plus omega IL is 2 omega IL, which is exactly omega. Okay, so that is the first step. The second step is I need to get the indices to match. So I will write this equation as omega KL times VI JKL. By the way, my convention is always to put a hat on all the operators, which I've conveniently ignored in this calculation simply because there is too many operators and it's a little laborious. But always understand that B and J are operators, so they should be understood with the hat on top. 1/2. Now I can write this as delta IK omega KL. Why? Because delta IK omega KL is simply omega IL. And what's the next term? I can understand this as minus how should I do this? Omega Li. Sorry, give me a second. No, I skipped some steps. Sorry. So I'll be a little more careful here. I shouldn't write it this way because one of the indices is already matched. So I will write it in a slightly general way. I will write the right hand side as omega IJVJ. Okay. Because L is a dummy index on the left and the right that is summed over, I can always call it omega IJVJ, and I will write this as 1/2 omega IJ minus omega JIVJ. This is perfectly fair. Okay. So now I will make all the omegas to be omega KL. So if I want omega IJ to be omega KL, I should have the I match with the K and the J match with the L in the first term. So I should write down a delta IK times a delta JL omega KL. Okay, so please verify that delta IK times delta JL omega KL is nothing but omega IJ minus. Now omega JI means I want the J to match up with the K and I to match up with the L. So I can write this as delta JK delta IL omega KL. Okay. And now I can write this as, now I can pull out the omega KL times this combination of delta functions, delta IK, or rather Kronecker deltas, not delta functions, minus delta JK delta IL times VJ. Okay. Now if I look at the left hand side and the right hand side, I know that I have an omega KL out in the front. So if omega KL is arbitrary, the equation has to be true for any value of omega KL. So I can simply equate the coefficient of omega KL on the left and the right, and the two cancels. So I have I over H bar times the commutator of VI and JKL equals delta IK delta JL times VJ minus delta JK delta IL times VJ, which is equal to delta IK, delta JL times VJ is nothing but VL minus delta JK times VJ is nothing but VK. So I can write this as IL. Okay. So now I have transformed this equation that talked about finite rotations into a commutator between V and J by applying it to an infinitesimal transformation. So this commutation relation again is given by I over H bar VI JKL equals delta IKVL minus delta IL. This is a very important relation. And even though this doesn't look very familiar, by the end of the class, I'll convert this into something that does look familiar to you from your study of orbital angle. Okay. So the reason I went through all these steps here is because there is another calculation that one can do and one should do, and I will give this as a tutorial problem for the next week. One can do a similar calculation to understand the commutators between J and J itself. Okay, now this might seem surprising. How can an operator commute with itself? But notice that if you have an operator that has many different components, such an operator can have a commutation relation with itself. And you are used to such an operator. The operator that you're used to is orbital angular momentum. So remember that Li Lj for orbital angular momentum is equal to IH bar epsilon ijk Lk. Right? This is something we used extensively in the last semester. And this simply means that there is no inconsistency in this relation, since there are different components of L, different rotations along different around different axes may or may not commute. In general, they do not commute. Okay. So this is simply a reflection of that. So similarly, you can also ask if the different components of J commute, and the answer is it doesn't. How do you get what the commutator is? Well, you again go from a fundamental relation. What is a fundamental relation? The fundamental relation is how does J transform under rotations. This is also exactly the same thing. This commutator is also a reflection of how does V transform under rotations. The way V transforms under rotations is like this, right? A rotation mixes the different components of V. So how does J transform under rotations? Well, J seems to be a slightly more complicated beast than V because it has two indices, not just one index, right? V only has one index, the vector index. It gives you what the component of V that we are talking about. But J has two indices. So how do I understand this two index of J? Well, the way you do this is, again, start by asking what happens if I sandwich J between two rotations. Okay. So suppose if I have something like this. And what is this equation? In the tutorial, we will show explicitly that this is a very interesting relation. J transforms under rotations as if we are talking about two different objects with two different vectorial objects with indices I and J. In other words, the I transforms like this, RILVL, and the J also transforms with another R. So what you have is something like this, RIK RJL JKL. Okay, what does this mean? This means that the index I in this equation transforms like the index I in this equation. Okay, in this equation. And the index J also transforms like another vector index, which means that Jij transforms like an object with two vector indices, and there is a name for such objects. They are called tensors. So Jij, so let me put a box around this equation before I forget. This is also a very important equation. So Jij transforms under rotations like a rank 2 tensor. Rank simply means the number of indices we are talking about. In this case, Jij has two indices, both of which transform like vector indices. So it is called a rank 2 tensor. Okay. So now, to get the commutation relations between Jij and something like JKL, you employ the exact same strategy. You assume that this rotation R that we're talking about is an infinitesimal transformation. You plug in the form of this infinitesimal transformation, and then you evaluate. And if you evaluate, and we will evaluate this explicitly, you will find the commutation relation you get as usual. This is knocking off. Give me a second. Sorry about that. So the commutation relation of J with J can be derived to be, this is slightly more complicated, minus delta IL JKJ. Remember that the left-hand side is an object with 4 free indices, so the right-hand side should also be an object with 4 free indices, plus delta IK JLJ plus delta JK JIL minus delta JL JIK. And for those of you who would study field theory next semester, you would actually find something very, very similar for the generators of Lorentz transformations. So the ij would be mu nu, the space-time indices, and the deltas would become g mu nus, the metric tensor. So apart from these two changes, this commutation relation exactly goes through. So there is something more fundamental about commutation relations in general. I don't have time to go into this very, very interesting aspect of it because it'll take me into the difference between Lie groups and Lie algebras. But notice that this is actually very, very fundamental. The commutation relations do not change. If you change axes, if you change whatever you use to describe the system, commutation relations between generators are fundamental in nature. Okay. So again, if this sounds a little, this second boxed equation sounds a little crazy to you, don't worry about this. We will derive this during the tutorial lecture. Okay. So thus far, what have we done? We have simply taken a general rotation element in the Hilbert space and then specialized it to a very specific infinitesimal rotation and then asked ourselves, how do different objects transform under such a rotation? Now remember that any physical rotation R in the XYZ or whatever a dimensional space is realized as a unitary transformation in the Hilbert space on the states. But equivalently, I can also understand the action of these generators on the operators in the Hilbert space. Okay, so this statement is about operators. So how does this rotation in the physical space induce an operator, and how do the other operators respond to this operator? All right. So now that we have extracted as much information as possible, I would like to clean up my notation by specializing to 3 dimensions because we will be doing quantum mechanics in 3 dimensions anyway. So in 3 dimensions, there are only 3 rotations possible. The rotations that are possible are rotations around the 1 axis, 2 axis, and 3 axis. So there is only 3 J's. The J's are J12, J23, and J13, or rather 3, just to be simple. Okay. J12 is a rotation in the 1-2 plane, which means it is a rotation around the 3 axis. So I will call this to be J3. J23 is a rotation in the 2-3 plane, which means it's a rotation around the 1 axis. And J31 is a rotation on the 3-1 plane, which means it is a rotation around the 2 axis. These 3 identifications can be formalized mathematically by writing Jij is equal to epsilon ijk jk. Okay. If you don't believe me, let us evaluate this for a particular value of k. So let us talk about J3. So J12 equals epsilon 1-2 k jk, right? So I've put I equals 1 and j equals 2, but since epsilon is a completely antisymmetric index, k cannot repeat itself, so k cannot be 1 or 2. The only value of k is equal to 3, so this is equal to epsilon 1, 2, 3, j3. And epsilon 1, 2, 3 is plus 1, so this is equal to j3, and so on and so forth. Okay. So this relation should be fairly easy to understand. I can actually invert this relation and I can actually write jk is equal to 1/2 excuse me, epsilon ijk jij. Okay, again, this is also something that you can easily convince yourself is true. If you don't believe me, let us evaluate this for a particular value of k. So let us call this J3. Put k equal to 3. What is the right hand side? This is equal to 1/2 epsilon I J3 Jij. So one of the indices is fixed. So I can be 1, J can be 2, or I can be 2, or J can be 1. So I have two possible combinations. So this is equal to epsilon 1, 2, 3 J12 plus 1/2 epsilon 2, 1, 3 J21. But this is equal to 1/2 epsilon 1, 2, 3 is just 1. So this is 1/2 J12. Epsilon 2, 1, 3 can be written as minus epsilon 1, 2, 3. And J21 can be written as minus J12. So the two minuses cancel and you will have 1, 2. So this is just J12. Okay. So which is precisely this guy. So both these relations can be easily understood in that sense. So moving on. So we will adopt the simplified notation in 3 dimensions where I will simply call J12 as J3, J23 as J1, and J31 as J2. Once I do that, what does my infinitesimal rotation become? This is equal to I plus I over 2h bar omega ij jij, but this is equal to I plus excuse me, I over 2h bar omega ij. Again, I will do the exact same thing for omega ij also. I will write omega ij is epsilon ijk omega k, because in 3 dimensions I only have 3 rotation angles also possible. So I can write this as epsilon ij k omega k, and jij I can write as epsilon ij. I cannot use k because I've already used, so I'll use a different index, L, JL. But you can use the fact that epsilon ijk times epsilon ijl is nothing but 2 delta kl in 3 dimensions. So u of omega can be written as I plus I over h bar, because the 2 in the bottom cancels the 2 up here, which was the reason for choosing I over 2h bar initially. Omega k jk. Okay, or this can be written as I over h bar omega dot j as a vector, where omega is understood as a vector with components omega 1, omega 2, omega 3, and j is a vector with components j1, j2, j3. Whether you write it as an index form as omega I, omega k, jk, or write it as a dot product, it's the exact same. So in 3 dimensions, we have arrived at a very simplified form for u because there is only 3 rotation angles possible. So how do the commutation relations look like? So again, I will do the commutation relation between j and v, and I invite you to do the commutation relation between j and j, but I will write down what the answer is. So let us recap what our commutation relation between v and j is. I can write this as I over h bar vk jij equals delta ik vj minus delta jk vi. Okay, so what is this equal to? So I will plug in j. So jij is equal to epsilon ij. Let's call L JL in this equation. So this is equal to I over h bar vk epsilon ijl jl equals delta ik vj minus delta jk vi. The epsilon has nothing to do with the commutation, so I can pull this commutation relation out. Sorry, I can pull the epsilon tensor out and write this as IJL VKJL is delta IKVJ minus delta JKVI. Now I will do a small trick. I'll multiply both sides by epsilon. Remember that I and J and K are free indices in this equation, and L is summed over. Okay. The left hand side, again, I, J, and K are free indices. So I cannot multiply with any epsilon that is a function of I and J, but I can multiply it with, I cannot multiply it with any epsilon that is L dependent because L is already summed over, but I can multiply with something that is I, J, but I will choose instead of L, I will choose some N. I, J, L. Now the reason I do this will become apparent in just 1 second. I, J, M delta I, K, V, J minus I, J, M delta J, K, V, I. Again, the left hand side is epsilon ij, epsilon ij is 2 delta ml. So this is 2 delta ml vkjl equals the delta ik forces I to be equal to k. So I get kjmvj, and the delta jk forces the k to be equal to j. So this I can write as epsilon I KMVI. Okay. And if you clear this up, which is in just 2 steps, you will actually get the beautiful relation JI VJ equals IH bar epsilon IJK VK. Now this form should be familiar to you because this exactly looks like the commutation relation of any vector operator with Li, the orbital angular momentum. So remember that the commutator of Li and Vj is also equal to IH bar epsilon Ijk Vk. So the commutation relation of J is exactly like the commutation relation of L. So the question is now, why introduce all this J business? I'll answer this question probably tomorrow. But before that, let us push ahead and tell you that if I substitute Jij, if I substitute this relation, Jij equals epsilon ijk jk in the boxed equation before, in the commutator between Jij and jkl, you will get the commutator between 2 different components of J also. So use the fact that Jij equals in Jij jkl to get Ji jj equals IH bar epsilon IJK jk. Okay. So again, this is simply using the factor in 3 dimensions. I only have 3 rotation angles, so I don't have to use a complicated rotation for J. So I can simply say Jij is just epsilon IJK times jk. And if I use this relation in this general commutation relation between Jij and jkl, I end up with a commutation relation of angular momentum generators. And this looks like Ji jj equals IH bar epsilon IJK jk, which looks exactly similar to the commutation relation between Li and Lj. So remember from last semester that the commutator of Li with Vj was also equal to Vk, and the commutator of Li with Lj was equal to Ijk Lk. Okay. So we will take these 4 equations as the starting point to introduce a new kind of angular momentum. But I don't want to do this today because I see that many of you are not around. So I will introduce this new kind of angular momentum tomorrow morning. And we will move on to the subject of understanding the Hilbert space of understanding basically the eigenvalues and eigen vectors of J square and J3, similar to what we did for L square and L3. Okay, so this will be our homework for tomorrow morning. But for now, I will stop and please ask me if there is any questions.